Let's look at 6.3b, binomial distributions. So how to calculate binomial distribution probabilities using the calculator. So you will go to second vars, which is the distribution, choose binomial PDF or binomial CDF, enter the trials, p-value, and x-value. So this is what it'll look like. Binomial PDF is if they are asking for a specific value. So x equals k. Think perfect. P for perfect number. C is cumulative. So you are adding up all the values at that number or less than. If we have to go greater than, we'll have to do 1 minus up front. But I also want to show you this on Desmos. So let's go to Desmos. So go to Inference, Probability Distribution. I'm going to pick binomial. So let's say I have 10 trials, probability of success is 0.25, and it creates the value. If I want a specific value, I just click. So let's say x equals 2, I just click that value. X equals 3, x equals 4. You don't have to go through and do it all those times. All you do is click. Cumulative, let's say you want to go less than 2, then you would pick left. If you want to go greater than, you pick right. And if you want to go between two values, you can click inner or outer. If you want outside of, let's say, less than 1, but greater than 5. So see how it shows up on that? Super cool. And you can also see the shape on here. So that's what I love about Desmos. All right, let's go back. All right, so here is, of course, our calculator. You can use either one, whichever one you enjoy better. I am probably going to do a lot of Desmos, but if y'all ask for calculator, I will do that for you too. Okay, so for the roulette example, we have n equals 10. The p-value is 18 out of, I think it's 38. So there's a typo right there. Let me fix that real quick. 18 out of 38. There we go. And we have x equals 4. So we'd go binomial PDF, put in n, p, x equals 4 to get that value. But let's say we want greater than 8. We would have to do 1 minus x is less than 7. I'm going to show you all that in Desmos. Okay, so we would have binomial distribution. 10 is our n. P is our probability of success, 18 out of 38. And that problem wanted us to say x is greater than 8. So we could do it like the calculator says, but this is just more intuitive. Greater than or equal to 8. I put that there. I can click this so I can see my probability distribution. And then if I want to see more digits, I can click this, and that shows me more digits. Okay. So let's go back. So that was the same value there. If you're using the calculator, you do have to do 1 minus. Okay, is it okay to use binomial PDF and CDF commands on the AP exam? Yes, but you must specify which one you used and label x equals the number of success. In trials, P probability of success. No labels, no credit. There is something you have to do if you're using Desmos as well. You want to make sure you do in trials, P probability of success, and what we're talking about for x, what x is. So it's the same thing. So how can you calculate the mean and standard deviation of a binomial distribution? Here are the formulas. Mu equals n times p, and then that is our mean, our expected value. And then our standard deviation is found by doing square root of n times p times 1 minus p. That 1 minus p is our complement. And these are on the formula chart, so that's good. So let x equal the number of the next 10 spins of a roulette wheel that land on black. Calculate and interpret the mean and standard deviation of x. So n was 10, p was the 18 out of 38. So then we just multiply those, and we get 4.74. And we will need to interpret this. So here is the template. If we spend 10 times over and over, or you can put many, many times, we can expect to land on black 4.74 times. That's what we will expect to happen. Standard deviation, plug in the values in P and 1 minus P. We get 1.58. We need to interpret this as well. If we spin 10 times, many, many times, there's an essay, the number of black spins will vary about 1.58 from the mean of 4.74. Okay, B, how often will the number of spins that land on black be within 1 standard deviation of the mean? So we've got to figure out what 1 standard deviation from the mean is. So you would go above and below the standard deviation of by the standard deviation from the mean. So we'd want to do 4.74 minus 1.58 and 4.74 plus 1.58. And so we'd get these values, 3.16 and 6.32. So if we do Desmos over this, go here, go to inference, probability distribution, binomial. How many trials are we doing? I think it's the same, isn't it? It's 10. And then success is that 18 out of 38, which is black. Create. You want cumulative. So we want it between 3.16 and 6.32. So 3.16, 6.32. Okay. And we get this value, 0.649. So it's all the values in between and including 3.16 and 6.42. Okay. So that is with Desmos. So let me show you with the calculator. So this is cumulative. So we would want to find the full amount to the left, 6.32 to the left, so less than, and then subtract the x is less than 3.16 because we want what's in between them. So it's the overlap is what we want. And so we would need to write this down. We need to write that down and subtract them. And we get the same value. So which would you rather do? This or that? It's up to you. Okay. All right. When is it okay to use a binomial distribution when sampling without replacement? Why is this an issue? So this is called the 10% condition. Almost all real-world sampling is without replacement, which violates independence condition. So most of the time we don't do, we do without replacement. So we'll take some Skittles out and then we don't return them. So when does this become a non-issue? Because we don't want to violate the independence condition. So the thing is, as long as the population is much larger than the sample, it's okay. And you're going to see this in class. So what does that mean? What it means is 10%. So sample is at most 10% of the population. As long as that happens, then you're okay to say that it's independent and just carry on. So the way we look at this is this is our sample. Oh, let me back it up. The little n is our sample. The big N is our population. So as long as the sample size is at most or less than or equal to 1/10 of n, then we're good. We're good to go. Okay, so our example is a cereal company that put out one of 5 different cards in each cereal box. Each card featured a different driver: Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, and Jimmy Johnson. Suppose that the company printed 20,000 of each card. So there were 100,000 boxes of cereal with a card inside. If a person bought 6 boxes at random, what's probably getting 2 Danica cards? So let's figure out what X is. So X is going to be the number of Danica cards from 6 different cereal boxes. And we want the probability of getting 2. So that's what we're going to look at. But before we begin, let's check bins, because we're thinking that this is binomial, because they want us to find the probability of getting exactly 2 if they bought 6 boxes. So bins. Probability of success, getting a Danica card. Fail, not getting a Danica card. I, sampling without replacement. But since 6 is our sample size, it tells us 6, and there are 10,000 total boxes, then this should be 10,000 of P. 10% of P, which is 10,000. So 6 is less than or equal to 10,000, which is 10% of our total population. That condition's met, so it's a non-issue that it's not independent. In 6 different boxes, S, probability of success, P equals 0.2. It says 5 different cards in each cereal box, and there are 1, 2, 3, 4, 5, so 1 out of 5. Okay, so let's write our probability down. Probability that X equals 2. So the formula is 6, choose 2. And then we do our probability of success, 0.2 to the second power, and 0.8 to the fourth power. So we can do this and put that straight into the calculator, or we can do our binomial PDF in the calculator, and this is what we get. Or we can put this into Desmos. Let's see, it is 6. Probability of success is 0.2. And we want exactly 2. So I don't even need to change this. I'm going to make that go away. I'm just going to pick 2. There it is. So I didn't even need to click that one. I just need to click this one. Super cool. Okay, so we do need to summarize this. So there is about a 24.58% probability of finding 2 Danica cards out of the 6 cereal boxes chosen randomly. All right, so that is it for today's lesson. This is all the binomial probability information. See you in class.